I will present analysis examples of using city-level heat mortality outputs to examine modifying factors, including city-level socioeconomic and demographic factors and city-level green space. These are the two manuscripts that resulted from this work, and I'll focus on each of them separately. In general, vulnerability to non-optimal temperatures is understood as a function of exposure, physiological sensitivity, and adaptive capacity of the population. From the epidemiological literature, we know that the relationship between heat and cold exposure and the resulting mortality associated with these suboptimal temperatures may actually be modified by a wide array of individual level and area level factors, including income inequality, poverty, living condition, education, and so forth. However, the conclusive evidence regarding the direction of these effect modifications is not actually that well presented in the literature, and the evidence is particularly sparse in Latin America, which is generally underrepresented in this line of work. The first example involves the analysis of effect modification of temperature-related mortality by city-level socioeconomic and demographic factors. And for this study, we use the same 325 cities as Josiah used in the study that he led, as well as the same daily temperature and mortality data. However, the new data that the study brings are the city-level census and survey variables describing the city-level socioeconomic and demographic effect modifiers. So these data, as you can infer from the name, were obtained from country-specific census and surveys. The specific socioeconomic and demographic effect modifiers that we chose were city population, population density, percent of the elderly population in the city, percentage of built-up area, age standardized mortality rate, living conditions score, secondary education, poverty, the Gini index of income inequality, and a measure of residential segregation based on the isolation index. The heat and cold excess death fractions that were obtained from the study that Josiah led were used as inputs or dependent variables for our work. And so in our study, we estimated associations between heat and cold excess death fractions and socioeconomic and demographic effect modifiers at the city level. In order to do that, we employed a random effects meta-regressions to evaluate those associations, and we fit separate meta-regressions for each effect modifier and heat and cold related mortality. The socioeconomic and demographic effect modifiers were modeled as three-level categorical variables split at tertile cutoffs in order to consider potential nonlinear effects. And the meta-regression suggested for indicators for countries, average daily temperature, temperature range, and climate zone. We also explored some additional analyses of effect modification, including mortality attributable to extreme heat and extreme cold, so just in addition to just cold and just heat. We also looked at temperature-related mortality for those 65 and older. We separately looked at cardiovascular mortality in addition to all age, all cause mortality. And we also stratified cities into climate zones in order to see whether the effect modification patterns may differ depending on whether a city is located in arid, tropical, or temperate climate zone. This slide will show associations between city-level socioeconomic and demographic characteristics and cold and heat excess death fractions. Now, on the y-axis, you can see all the city-specific socioeconomic and demographic effect modifiers that we used, and the effect estimates that I'll present can be interpreted as percentage point differences in heat or cold EDFs associated with differences in city characteristics. The reference category for each of the effect modifier and for each of the estimate are the cities with desirable level of socioeconomic modifiers, for example, cities with high living conditions score or cities with low poverty. For the population density, and percentage buildup area, the reference category are cities with the low absolute value, so the bottom tertile of the distribution of these respective variables. Now, you can see the actual effect modification estimates and their confidence intervals. And what you can see for cold is that, and heat as well, is that the overwhelming majority of these effect estimates contain the null. What we see, however, for cold is that in cities with high inequality, we expect to see cold-related mortality that is on average about 3.5 percentage points higher than in cities with low income inequality. However, if we look at heat excess diffractions, we see several puzzling associations, in particular for poverty and the Gini index. So you can see that for heat, the effect estimate for the Gini goes in the opposite direction, meaning that in cities with high income inequality, on average, we see heat EDFs that are actually lower than in cities with low income inequality. And the same interpretation can be used to describe the effect modification that we see for poverty. So it also goes in the unexpected direction. Now, on this slide, you can see effect modification of the relative risk of mortality. And just to briefly remind you, by the relative risk of mortality here, we are talking about the steepness of that curve, of the temperature mortality curve in its highest and lowest absolute regions. So specifically, the estimates that I will show can be interpreted as differences in the relative risk of mortality associated with a 1 degree Celsius increase in mean daily temperature above the 95th percentile of the city-specific temperature distribution. That would be the interpretation for the interaction relative risk for heat. The interaction relative risk for cold can be interpreted as a difference in the relative risk of mortality associated with a 1 degree Celsius lower mean daily temperature below the 5th percentile of the city-specific temperature distribution. And as you can see from these interaction relative risk estimates, the overwhelming majority, if not all of them, actually contain the null. So we don't really see any clear patterns of effect modification of the relative risk of mortality by city level, socioeconomic, and demographic factors. Just to summarize the results, what we find is that there is limited evidence of effect modification of cold-related mortality by city-level factors in Latin America, and we find several unexpected associations for heat-related mortality, including that cities with high levels of poverty and high levels of income inequality experience smaller heat-related mortality compared to cities with desirable poverty and income inequality levels. We also observe that higher poverty and higher segregation are associated with higher cold-related mortality among those 65 and older, and we don't see evidence of effect modification for cardiovascular mortality and by climate zones. The second analysis example includes modification of heat-related mortality by city-level green space. In general, it is accepted in the literature that green space may be associated with human health and well-being via a number of different pathways. The first pathway is the reduction of harm or mitigation pathway, wherein green space can reduce exposure to environmental stressors such as air pollution, noise, and heat. At the same time, green space can also be helpful for restoring attention and aiding in psychophysiological stress recovery. Finally, green space can also encourage physical activity and facilitate social cohesion. In this study, however, we are interested in this first pathway, or the reduction of harm or mitigation pathway, where we hypothesize that the potential beneficial effect of abundant green space in cities for heat-related mortality occurs through the ability of green space to provide cooling. And indeed, this pathway is something that has already been observed in the epidemiological literature. But in addition, we're also interested in how other features of green space, besides its amount, so say how it's distributed across space and how it's arranged, are also related to heat-related mortality. So the data that we used in the study is very similar to the data that we used in the previous example. The only difference is that here we bring in another exposure data based on green space. And the first data set is the normalized difference vegetation index that was obtained from the MODIS instrument of the Terra satellite. These data were available at 250 meter spatial resolution, and it was available every 16 days. The second source of green space data represented Sentinel-2 images, which were classified to represent whether every pixel was considered green space or not. And then based on this green space land cover map, we computed various measures of landscape characteristics of green space. So the first measure of greenness that we used was the area level greenness represented by city level normalized difference vegetation index. The NDVI measures the amount and intensity of vegetation, and we computed the annual maximum NDVI for every pixel within the city. After we computed the annual max NDVI for every pixel, we obtained the median of the annual maximum NDVI value for every city to capture the peak vegetation growth. So the final city level metric was the median of the annual maximum NDVI for every city. And the interpretation of NDVI is that higher NDVI values mean more abundant and verdant vegetation. The second measure that we focused on can be described as a measure of green space clustering, and it is based on a landscape ecology measure called clumpiness index, which captures the extent of aggregation of green space across a landscape. It ranges from -1 to 1, with -1 denoting maximum disaggregation, 0 meaning random distribution, and 1 meaning maximum clustering. And you can see examples of high and low green space clustering in these images below. So just like in the previous example, we used the estimates of heat and cold excess death fractions from MS85 as input for this work. And in particular here, we only focus on heat excess death fractions. And then what we did in this study, we estimated associations between heat excess death fractions and city level green space. In order to do so, we estimated random effects meta-regressions between green space and heat EDFs. These meta-regressions were stratified by climate zone, specifically arid versus non-arid climate zone, in order to account for the fact that the kind of green space that is available in arid cities is very different compared to non-arid cities. And you can think of examples such as cacti and succulents that are usually not very green in general, but they're also quite low in terms of their height. So in order to account for that, we stratified cities in arid and non-arid categories. We modeled greenness as a 3-level categorical term with categories based on the tertiles of the climate zone specific distribution. All of the meta-regressions adjusted for city PM2.5 concentration, the social environment index, and a country indicator. And as a final step of our analysis, we estimated effect modification of the association between heat-related mortality and greenness by green space clustering. And to do that, we included an interaction term between a 3-level categorical NDVI variable and a dichotomous clustering variable, which was split at the median. This slide contains results from the random effects meta-regression estimates of the association between NDVI and heat excess death fractions stratified by climate zones. These estimates can be interpreted as differences in heat EDFs between cities with high and moderate levels of greenness relative to the cities with low levels of greenness in arid and non-arid climate zones. And what we can see from these results is that among the arid cities, cities with high levels of greenness show incrementally smaller heat EDFs than arid cities with low levels of greenness. However, the confidence interval for that estimate contains the null. For the non-arid cities, the betas are closer to the null and their confidence intervals are quite wide, so we can't really say that we see any pattern of effect modification of heat-related mortality by area level greenness in the non-arid cities. Here you can see results of effect modification of heat-related mortality by an interaction between green space amount and its clustering. And again, these results are also stratified by arid and non-arid cities. So what we see in arid cities is that there may be some protective associations between high greenness and heat EDFs in those cities that have low levels of green space clustering. For example, in arid cities with lower levels of green space clustering, the cities with the highest levels of greenness have on average 1.27 percentage point lower heat EDFs compared to cities with the lowest levels of greenness. And if you look at the effect estimates for the arid cities with higher levels of green space clustering, we don't really see evidence of effect modification there. And we don't see evidence of interaction between greenness and green space clustering in non-arid cities as exemplified by the likelihood ratio tests. So to conclude, we find that higher city level greenness is associated with modest protection against heat-related death in arid cities, and this especially may be the case in cities with distributed rather than clustered green space. This can be the case because vegetation in hot and dry climates has greater cooling capacity compared to humid climate zones. Now, our finding of less clustered green space that may be more protective against heat-related mortality is consistent with some, but not all exposure studies. For example, there was a study from Phoenix, Arizona that showed that higher levels of green space clustering was associated with enhanced cooling at a highly localized level, whereas less clustered green space had greater regional cooling effects. So there may be some implications of the configuration of the green space in space for cooling, which may depend on spatial scale. So now we've seen two examples of the effect modification analysis, and I would like to conclude this presentation by providing a brief summary of the lessons we learned, including the strengths and the challenges that we observed in our approach. So our large sample of Latin American cities fills a geographical gap in this research on temperature-related mortality and its effect modification outside of the global north countries. And because of that, we now have a better understanding of the magnitude and the effect modifiers of cold and heat-related mortality in tropical and arid regions that have different temperature and climate regimes and that have so far been quite underrepresented in this line of work. We also, as I mentioned before, we also have a large sample of the cities in Latin American countries, which is great because we represent the entirety of the Latin American region. And we also have high quality measures of the temperature and green space exposure. In addition, our green space metrics not only describe the amount of vegetation, but they can also describe how it's distributed across the cities, and we also rely on state-of-the-art and robust statistical methods. The challenges I would like to mention are mostly related to the fact that we use city-level measures and city-level analysis that mask a lot of heterogeneity in temperature-related mortality. For example, we don't have data on proximity of green space to people's residences, and that stems from the fact that we use city level measures of green space exposure. We also do not account for within city differences in temperature in green space, and what I think is that a smaller geographical scale for the effect modification analysis could greatly help us explain some of the unexpected associations. Finally, we also did not consider the thermal comfort that is associated with our temperature exposure, and that could be helped by adding a measure of the relative humidity. Thank you.